How many online do you have that attend? You know?
3, 4.
Oh, really? Okay. Yeah.
Students about 8.
Yeah. Okay. Yeah. You know, I teach process control and I've had several students that have gone away on, you know, co-op or internships that want to take it while they're off campus. And so I do that, you know, I do it as a, you know, favor for them. And some of them are really good, you know, and they'll join and they'll participate, but mostly not. Perfect. Thank you. But mostly not. It's hard when you have online students. Yeah.
But there's expectation in some sense.
Yeah. Yeah, that's right. You know, and it's so interesting. There are some schools that have huge online programs. I mean, Arizona State, it's like 300,000. Can you imagine that? 300,000. It's crazy. So
You're going to dinner, I guess, but you have seen the itinerary.
is that?
You have seen your itinerary after this.
Yeah. I've got about 4 copies of it, different versions. So
I noted that Sarah was gonna walk you to
yeah,
the hotel and tell her that, you know the campus, you meet.
yeah, I can find it.
She might show up at 4:50 or so.
Yeah. Yeah. And so my challenge tonight or today is to get through these slides. So this is a version of what I showed in Morocco, but it's evolved since then. But it's got 40 slides in it. And so that's too many slides. I already know that. I need to rush through the first part of it. So I will tell them that. Women in nuclear. I love that. He says women in nuclear. Yeah.
So we have 3 organizations, society, like women and those graduate student advisory committees. They are both AMS chapter.
Yeah.
And women in nuclear. They got the best chapter award.
Did they?
So simultaneous, both of them on this chapter.
Wow. That's amazing.
Leave it them. They want to make it. You can talk about that.
Yeah, we're gonna do some electrical. I love it. Yeah. That is awesome. Yeah. Potential difference. Aha.
I think.
Have you ever sent Morse code?
I think so.
Yeah. When I was a kid, yeah. We learned it, right, for Boy Scouts. Mhm. Yeah.
But I think we should go ahead and start.
Yeah.
You have any start?
I'll just put it up after.
Okay, I was just told that the script has too many slides, so we should start on time, and hopefully other people who are still coming on every time and then coming here or coming here and looking for one for one, but let me start. So very fortunate to have Professor David Smith with us today. I've known him for several years, and I've been trying to see, like, to get him to, invite him to give a seminar for a few years. And finally, we're lucky that, he's made it today. And it's a joint, seminar today, being lived there at CRE, but it's TV. So maybe there may be some people here from chemical and biomolecular engineering. He has history actually at a conference. And he's extremely accomplished. I can read some of this. He has taught at Tennessee Tech, Michigan, and Illinois. And he's currently he was selected as the founding Wayne and Gabe Laufer Endowed Energy Chair at Missouri University of Science and Technology. And it was in that context that there was a energy symposium workshop that was held a couple of years ago in Rolla, where I was invited and I met him. And then later that same workshop was held last year in Morocco, where we again met. And it was a wonderful trip and wonderful workshop and conference around energy and sustainability. Lots of accomplishments, books, and so on. I will skip all of them. And so you can probably see the focus on the chemical side, energy, energy conflicts of the modular reactor. I don't know what he's going to talk about today, but it's written on CFT, and then on CFT, and also consulted with the oil and gas industry, and many other industrial connections. So,
Thank you. It's good to be here. It's good to be back in Illinois. My wife is actually an alumnus from here, and I was on the chemistry faculty. And when I was here, she was getting her degree in linguistics, and we were in the same college. I thought that was pretty cool, right? Arts and sciences, but there are not a lot of schools like Illinois. It's a unique school, and I'm grateful to be here. Thank you for the invitation. And today I'm going to talk about a serious issue that we face. This is a global issue, something that we all, as engineers, have a role to play in solving. And as the president this year, as in my presidential year of AICHE, which is equivalent approximately to ANS, right? We're trying to work on this together with a lot of other societies around the world. I was in Morocco with the Energy Symposium, as was mentioned, but earlier was in Prague and met with the European Federation of Chemical Engineers. And when I was in China this summer at the World Congress, we met with all of the societies from around the world. And this is one of the issues that we discussed. We hear a lot about climate change, and that is a global issue also. We need to find ways to reduce carbon emissions and, reduce temperature increase. And but along with that, it's not an either or, but it's an and. We have to find ways to provide electricity to the over 1 billion people that go to bed every night without electricity. And what that means in practical terms, 25 years less life expectancy. That's how serious it is. And I've been in these places. I've been in Nepal, and I have a graduate student from Nepal, and I went and stayed with his parents up in a small village at the foothills of the Himalayas. And I saw what it meant, as a elementary school student, my student that now works for Intel out in Albuquerque, but his mother would go without so that he could have electricity at night to study. And his whole family gave up so he could come to the US to study, right? I mean, it's a serious issue that we face. I was in Morocco, as was mentioned, and Africa is the main continent remaining in the world where they have critical energy poverty, where they have, very low income and very low access to electricity. Last year, and I'm going to show some of these results. Last year, I teach a class in energy and process intensification, and in chemical engineering, that's a big deal. Trying to reduce the number of unit operations in a chemical plant, right? And in that class, I have the students do projects, and one of the projects that I offered last year was competition in the switch competition, or participation in the switch competition, which is an international competition. And the winner, $10,000 prize. So how about that for a class project, right? The chance of making $10,000. Well, one of my teams that I was a mentor for won 5th place, and they got $1,000. Still not bad, right? $1,000 for doing a class project. But that's something that comes out of University of Texas, Austin. And again, encourage you all to look it up online and just switch, .com. You'll find it and to participate, because that competition is focused on this topic I'm going to talk about today. Now, I have to apologize in advance. I have way too many slides. Okay, I'm going to rush through the first part of the slides so I can spend some time at the end where I'm talking about Africa, and we're comparing 2 countries in Africa, Senegal and Namibia. And we're going to see, again, what energy poverty is, and then one way to solve it. Okay, so that's what I'm going to do today. And again, thank you for coming. I know this is a class. I understand chemical engineering, you've already had your seminar for today. And so you're here at your own choice. Thank you for coming. And I hope I don't disappoint you. Okay, so there you go. I'm going to talk a little bit about AICHE, 1 or 2 slides, and then we'll go into hybrid energy. And then we'll end up with some conclusions here after we talk about Africa and how do we use nuclear and hybrid to solve this problem. Okay. All right. Chemical engineers. As I mentioned, I'm the president. And so today we are in the middle of a search. Again, it's an international search for our CEO for AICHE. Kimmies, if you didn't know that, that's what's happening at the national level. And I'm, as president, on the search committee. And so we actually are looking at several really amazing candidates. But our mantra is we're the global home of chemical engineering, and we are trying to find ways to help support career development and growth for your, once you graduate from university. Societal contribution, again, process engineering. If I were to ask you what a process engineer does, how many of you could give me a 1-word answer? Yeah. Very few people understand what process engineering is. I'll give you a quick example to illustrate the point. In World War II, one of the big causes of death was malaria. And disease, it was a big issue, right, for the Allied forces. And they discovered, prior to World War II, penicillin, right? And you could probably look up online, you could Google it and find out who invented penicillin. But who, and again, the person that discovered penicillin, right, bioengineering, could make maybe 10 batches. And so maybe they could cure 10 people. But who was the person that made it possible to make 1 million batches? Yeah, Dr. Rousseau. She was a woman, chemical engineer, and she developed the process to commercialize this technology and make it available to society. Today, we take it for granted, but that was not a trivial invention. That was not a trivial contribution. And so in chemical engineering, process engineering is a big deal. And so we're trying to recognize and educate the public on what process engineering is. That's part of AICHE. And again, global challenges. We're involved in these global challenges, and we have to be, not just chemical engineers, but all engineers have to find ways to solve these difficult problems. And so that's AICHE. All right, so what is energy poverty? Let's talk just briefly about this, and then we'll move on. So the definition is there, but as I mentioned earlier, the bottom line is access to reliable, clean energy. And how do we make energy today? I mean, if you look at Illinois, where do you think Illinois gets more than half of their electricity? What would you say? Anybody? Comes from fossil energy. Still today. Coal, gas, fossil energy. There's a large fraction of nuclear. We get a lot of nuclear. DC Cook is here in this state, up to the top of the state. but there are several nuclear reactors in Illinois. But some wind, not as much as they have in Kansas or Texas or North Dakota, but some wind. And solar, we have solar. I have a nice solar system on my house. I drive a Tesla, and so I'm all about that. But energy poverty is the ability to provide that electricity for others. Now, what does it mean without that electricity? Well, when I was in Nepal, what I saw was they have no refrigeration. So in the morning when we had breakfast, my student, as we walked over to his aunt's house, he whispered to my wife and I, said, make sure you eat everything on your plate because it was prepared fresh this morning. And the reason is because they don't have any way to preserve it. And so they have to prepare everything every day. They go to the water buffalo, they milk it, they get the milk, and they provide the porridge, but that also means no drugs because pharmaceuticals have to be refrigerated. And so without electricity, you can't have that. That means more waterborne illnesses and shorter lifespan. So that's what I saw firsthand. All right, so in the world, if you think about this, the global population continues to march on. Today, what are we, about 8 billion people? And we're headed to 9 pretty quickly, yeah. Access to stable, affordable energy is the key to peace and prosperity. And that is a very real statement. Most of the wars, if you look at history, most of the wars that have been fought have been over energy. World War I, World War II, those are both energy wars. The civil war in Syria, that was an energy war. Iraq, those are energy wars. Access to energy is a big deal. And so if you have stable, affordable energy, you have peace and prosperity. That's the bottom line. And then the last thing is the growth as we look forward into the future is coming from the developing world, not the developed world. You look at the green and blue boxes there, you look at Europe, there's no growth. In the US, very little growth. Most of that growth comes from Africa, from Malaysia, from Asia, and so that's where the need is the greatest. And you'll see that in the news, around, something that we have to be able to address. All right, I mentioned this to you. These are pictures actually from Nepal and Kathmandu and that place, but a lot of people need this. Again, energy equity, this is a big deal. Energy equity, energy justice. There's pictures, again, of the students that study underneath the streetlights, right? How many of you go out under the streetlight to study? Probably none of you, because you have plenty of electricity, right? And again, this is a typical US refrigerator uses as much electricity in a year as 9 Ethiopians. So you all have refrigerators, yeah? To keep your dinners or your drinks or whatever cool. Yeah, 9 Ethiopians, yeah. World demand is estimated to increase by approximately 50% by 2040. So it's going up. And greenhouse gas emissions are proportional to energy use. That's because of where we get our energy from. Okay. All right. This is a big deal also. Again, I was shocked when I found out that the #1 cause of death in these developing countries is not tuberculosis or AIDS, it's health respiratory disease because of women, and it's predominantly for women because of the culture, but women cooking in enclosed kitchens like that's shown there with biomass, mostly dung or wood or something. When I was in Nepal, my wife went into the kitchen where my student's mom was cooking, and it was like she was choking when she came out, and because it was filled with smoke. Okay, so that's a big deal. So, UN Sustainability Goal 7, universal access to modern fuels by 2030 to mitigate household health effects of dirty fuel use, wood, charcoal, dung, kerosene, from household air pollution, and enable them to develop productive educational and self-fulfilling opportunities for women and girls foregone due to labor required to obtain use of such fuel. So that's a big deal. And you think about, equity, energy equity, and justice. All right, so here's a concept. This is one idea that actually was first developed or was first introduced at Idaho National Lab when I was there. These are hybrid energy systems. And this concept of combining is something that's, we all think about this because we're engineers. We think about how do we hybridize? How do we get more out of what we already have? This is the Sunflower Integrated Bioenergy Center in Kansas. And this is built around a coal plant. And so at the center here is this, it's about a 600 megawatt coal-fired power plant. But along with that coal, they have an algae reactor. It uses a CO2 from the coal. This generates electricity. That algae reactor then provides solids for the dairy, that provides manure to the anaerobic digester that produces methane. This also provides oil to the biodiesel plant that provides biodiesel and provides ethanol. So a hybrid system has multiple energy sources and multiple products that are produced. And by doing that, you're able to improve the economics and make it more sustainable, more resilient. Okay. And you think about world energy use. Look at this and compare. This is in 2007. This is world, 475 quads. A quad, you guys will probably recognize, one quad is 10 to the 15 BTUs. Okay, so 475 quads in 2007, and about 45% efficient and 81% fossil, right? 12% renewable. By 2011, that went up to 720, and the efficiency went down, and the percent fossil went up, and renewables went down. That's going the wrong direction, right? So here's China. Look at China in 2011, 110 quads, 42% efficient, 88% fossil, 10% renewable, 0.8% nuclear. Now that's changed a lot since 2011, but that's just a picture. Now here's the US, and again, this is 2019. So look at this, again, reduction in efficiency between 1970 and 2019. And look at the fossil use, again, that went from 98 down to 80, that's the right direction. And nuclear, 0.24 to 8.4. So we had the initial nuclear renaissance in the 70s, and then that resulted in having nuclear power here. But here's 2050. This is from IEA. This is the projection for 2050, 143 and 55% efficiency, so that's getting better. Fossil is still going down, but nuclear went down also. So I don't know if that's true or not, but that's what the agency estimates. Question is, fossil energy will remain our largest source. What can we do to reduce the impact on the climate? How do we fix that? Because it's something that we have to do, right? What role does imported petroleum have on in the economy? And again, right now, it's drill, baby, drill, right? Well, you can debate whether or not that's working or not. Gas prices, at least in Raleigh, haven't gone down. They're about where they were when we started that new concept. How about transportation? Again, I drove up here from Raleigh, my new 2025 Model 3 Tesla. Got a 360-mile range, right? So I didn't have to stop and charge along the way. What's going to happen in the future? The projections are that we'll become more electrified, not less. That means we'll have a higher demand for electricity, not less. Now, again, this is the estimates, and you can see the green ones are the ones that have increased, and so there's wind, there's bio and geothermal, solar, nuke, coal, and oil. So we'll see what happens, but that's what we're looking at as we talk about the future. Now, I want to show you something else that's really important for this energy question. This is a picture of the East Coast, Northeast. So there's Long Island, and there's Cape and Massachusetts. So this is New York, and down here is Philadelphia. This is in 2003, and we had a major blackout right here. All right, so let me just show you. That's what the lights look like after the blackout, after we lost power, and that was approximately 45 million customers that lost power. That's a big deal. So grid stability is also very important in grid design and how we address this issue. Okay, here's Texas. This is more recent than 2003. This is what happened in Texas, right? 2021. And this is the picture of the grids in the US. This is the Texas grid. There's the Western grid, the Eastern grid with the interlocks between each of those interconnects, I mean. And this is the grid outage in February 16. You can see the red are ones that lost most power. And there's a picture of Houston during this time. Now, when that happened, and it wasn't because we had too much solar or too much wind in Texas, it's because of the planning. It was a planning issue with fossil energy in Texas. That's what caused this grid outage. But it was a serious issue that happened. And spot prices went from $2 or $3 for natural gas to $100 to $200, okay, per million BTUs. All right, so again, here's Nepal now. This is comparison in the world. So here's in 2013, 2014, the total electricity consumed, the gigawatt hours, and then total generated. And what you should see here, this is what's purchased. Here's they're generated. So they purchase a lot because they don't have a lot of energy resource. Now you say, well, Nepal's got lots of mountains, right? Anybody been to base camp? Yeah, Himalayas. They got a lot of hydro, right? But the thing is that India controls that water, and so Nepal can't use it, or else they'd be at war with India. So, this is a big deal right there. This is, yeah. These are their other energy sources. So most of their electricity is generated from imported energy fuels. All right. So this is another concept that kind of is next generation of sunflower. That's one I showed you earlier, the hybrid system. This is a nuclear hybrid, and this is what is kind of the current thinking at Idaho National Lab. This is what they're working on, is how do you integrate small modular reactors with fossil fuels to reduce the amount of carbon emissions and produce fuel and chemicals. And so that's this concept of hybrid energy. And so small modulars. And so I know that Illinois is, and so are we, looking at putting a micro reactor on campus. And micros are small. Most small modular reactors were about, from 100 to, 225, I think, the Westinghouse small modular, but micros are 5 to 10. And so it's perfect for a small community like Rolla or Champaign. You could put a micro in here fairly easily, actually, to start to develop these hybrid systems. And these are the different places where SMR designs are being developed. And I have another switch competition team this year, and they're focused on Kazakhstan, and nuclear is what they're trying to promote. And so it's a Chinese design that they're looking at. And the Chinese are selling their SMRs at about $10 a watt. When you think about that compared to what we could get from one of the US providers. All right, so here's an SMR, and again, just show you some of the features of this. This system is inherently safe. It shuts down, without, if it loses power, there's no more Fukushimas. That would never happen with a small modular. This is kind of a general design, but they're all pretty much the same. The steam generator is, up in here. Here's the core down here. These are built underground, so they're inherently safer from security risks. And the the designs again range from micros to this one. This is about a 200 megawatt unit here. All right, so now let me jump now to the switch competition, and I'll see if I can get through these. Now, that's the team. Those are my students right there. They're out working now. They all got jobs. That's the objective, right, of students when you come to school. It's not to stay here. It's to get out and get a job. And so they're out working now. But this is the 2025. So what they were assigned to do was to look at 2 countries in Africa. So there's Africa. And they looked at Senegal, which is right up here, and Nambia, which is right down here. Okay, so here's South Africa. And in Africa, when you look at the energy generation, South Africa and North Africa mostly, but the central part of Africa is very impoverished in terms of energy. Okay, so and again, you see, in terms of, let me go back here, in terms of population in Senegal, it's about 18 million, and Nambia, about 2.6, 2.7 million. Okay, look at this, energy access, 74% in the city and 33% rural, and over here, 70% urban and 17. But this is the rural population, and they have lack of energy in those countries. Okay, so here we go. So these are the main issues. So Senegal, if you look at this, this rural area lacks access to reliable energy. They also have this over-reliance on imported energy, similar to Nepal. And they're highly dependent on biomass. And so biomass is good because it's sustainable, but they're just a limited amount, right? We're lucky here in the Midwest. We have lots of rain and we have good farmlands, and so we grow a lot of corn in Illinois. We grow corn in Missouri as well. We have a lot of bioethanol plants, right? Because of the corn. Iowa, have a lot of corn, but it's limited, right? Not so much in California or in Boston. Okay? All right, here's Nambia. Again, it's over-reliance on imported energy. It's another issue. And they get most of their energy from South Africa because they're right next door. But in both cases here, policy and regulation is a big deal. And it's the government. And there's a lot of corruption in the government. So that's one of the reasons that they struggle with having sufficient energy for their needs. Okay, accessibility. Here's the comparison between Senegal and Nambia in terms of electrification rates. Urban, there's high, electrification is 75%, but look at rural, it's only 17% of the people have access to electricity. And again, animal waste is a primary source for cooking, which is again the UN mandate there to try to fix this problem. Here in Nambia, 75 and 36. So this is a little bit better, and it's mostly imported from South Africa. Here's this reliability. And so you can see this blackouts and inadequate service. This is fossil and hydro and then other renewables. So not much in terms of renewable. And there's this huge gap between demand and growth. And in Nambia, they do have a lot of hydroelectric energy sources, but again, most of this is imported. And then affordability. And again, this is showing 5,000 kilowatts per month, right? And that's a unit price of electricity. So this is up to about 55 cents a kilowatt hour. What do we pay for electricity here in Champaign? Anybody know? What's your power bill? 18 cents. Okay. In Raleigh, it's 9 cents. So makes sense to drive a Tesla, right? Yeah. But 55 cents, right? In Senegal. Over here, you can see, again, this is high price, and it's coming down, right? You can see this changes with the season here, but all right. So the other issues that you have to think about, again, what's the impact of the environment and the quality of energy and the safety and security? So in Senegal, this high reliance on fossil fuels and the deforestation and biomass use, that's a big deal, right? They're already deserts. They're in the savanna region of Africa. And so they don't have, unlimited supply of biomass, which is what they're using. And these biomass fuels, again, there's issues related to this: air pollution, community health, and then vandalism and natural disasters. Those are all related to that fuel right there. And then financial constraints. One of the challenges that the developing world faces, that we as a developed country have to face, is the economic inequalities. We have a quality of life, that is here, and in Africa it's here. And so they can't afford to put in expensive, energy systems that we rely on. And we then tell them that they can't use fossil fuel because it's going to affect the climate. And fossil fuel is the cheapest if we were going to fix the problem. So how do we deal with that financial inequality? That's a big deal. In Namibia, again, one of the big resources that they have is uranium and copper. They have a lot of resource there. And so that's where they get most of their income in their balance of trade. They also have new oil discoveries in Namibia, and they unfortunately have this aging infrastructure and political uncertainties. So these are some of the other issues that these two countries face. So if you look at those criteria in terms of energy poverty, right, and you rate them, we picked Namibia as the one that we would focus on. Now, let's figure out a solution. How can we fix this problem, right? So if you look at this, in terms of energy source ranking, right? So here are the different types of energy: solar, hydro, nuclear, fossil, and wind. And give these ratings, 1 through 5 here. And this was ranked number 1 because portability, power generation, ease of access. So solar makes a lot of sense in Namibia, right? And so how do you put that in? What's an effective way to do that? Well, what we had proposed, and this is something that we have done with University of Illinois, actually, we've had joint projects to investigate the use of microgrids. And so these are small grids instead of the large national grid, and you can have solar generators that provide energy to a region, so maybe 100 homes. And these are a picture of our microgrid in Rolla, and these are homes that students live in, and these are all homes that were developed for the solar decathlon that the DOE sponsored. And so we would bring them back from the competition and put them in there. And so we actually have built a microgrid that has real life load profiles because students live there. And so we know in the morning when they're getting up and they're drying their hair or they're taking a shower, we know what the energy usages are. And so then we can build models from that in order to develop projections and building microgrids in other places. The other thing that this has allowed us to do is to develop low-cost housing. And so this is actually built out of containers. And so they look pretty cool, but they were designed from a container that it's a lot cheaper to build a container home than it is to build from stick. And they're small, they're not huge. They're 1 bedroom, 1 bath. The solar, again, provides about 8 kilowatt hours. And they also have solar thermal to provide hot water and so forth. They're very energy efficient systems. So this is what we have proposed again in Nambia. So this is again the microgrid. And so here's the storage device here, the generator. This is a gas generator, and then vehicles, and then the controller, and then power sources, solar and wind, and then the macro grid. So we can actually, in that microgrid in Rolla, we can turn it on and turn it off from the national grid. And that means we can island it. And so in Nambia, that's what they can do. They don't have to rely on a national grid in order to operate these systems. And again, this is remote access. And so from Champaign, they can access that microgrid and they can monitor the load. And that's what the project was that was funded by ARPA-E. All right, so here's some of the issues to consider that we have thought about. So location. There's high energy demand in urban areas, right? And I said the urban area in Nambia already has about 85% electrification. So in the rural area, they had like 17%. And so this is a big deal. Location, design, again, dependent on the country's supply and load profile. And so that's something that we have to gather to design something for the system in Nambia. Financing, how do we provide financing for these, to build these systems? They're not that inexpensive. They're pretty expensive, but Nambia has uranium and fossil fuels as a basis for their financing. And then leverage, can we leverage against ongoing projects in Africa? And it turns out that there are right now, they're either funded by the World Bank or by the UN, these projects that are focused on building green hydrogen or African microgrid projects. And so these are some examples of projects that are ongoing right now and in Nambia. All right, so where can we implement these? So again, look for the regions with high energy poverty and proximity to existing resources, and then overlap of energy intensive locations. So that we actually studied this and looked at the the coast, this region right here of Nambia and so each of these boxes would represent an area that we could implement one of these microgrids. And this is the uranium. So again, here's the resource that that Nambia has access to. And again, South Africa, right next door, has nuclear reactors, and so they have a demand for that. And so they have already an established trade agreement between the countries. All right, so we can develop this to provide 28 megawatts per day for 1,000 people for residential and power needs. That's what we determined was the load that would be required for this microgrid. And the solar farm required to support that was about 26 acres, which is not a huge solar farm. Other places in China and in other parts of Africa, Morocco, for example, they have solar farms that are 10 or 15 square miles. They're big solar farms. So 26 acres is not that large of a system. Estimated costs for these microgrids are about $13 million US per microgrid installation. As I said, it's not inexpensive, but it can be funded by access to those natural resources. And again, this is the type of system. Battery backup, this is just a power wall by Tesla. There are others. The solar system I have at my house is 11.8 kilowatt hours generation capacity, and it doesn't have a battery system. It has gas backup. And so it's like an infinite battery, right? If I lose power and the solar doesn't generate enough electricity for my house, then the gas generator comes on and makes up the excess. And so they could do the same thing here because they have gas in Nambia. All right, costs and financing. So the solar farm, these are the different parts of this system, about 4.7 million US, and the battery storage is the most expensive part here, infrastructure costs, and then the total cost about $13 million. These two programs that are ongoing right now provide resources to finance that type of an expense to help to eliminate energy poverty in Nambia. So these are the issues that are addressed with a microgrid solution. Proper storage capacities reduce dependence on the primary grid, and then access to energy increases the number of residents and economic activity. It's actually interesting when you have access to electricity and a reliable, clean resource, then economic activity increases. And so now you move up on the ladder, the economic ladder. And so it not only provides electricity to help improve health and help improve, you know, address energy poverty, but it actually helps to increase the economic performance in the area. These communities actually become self-sufficient, which attracts new businesses, and residents can live closer to work, which reduce transportation costs, which is also a big deal for places like in Bia. All right, so here are these programs. I just want to just quickly, and I'll be done here. The African Mini Grid project, right, has uh, uh, these 1, 2, and 4 that allow it to support these 18 initial projects. And this is policy and regulation. This is the first thing that they address in this AMB project is how do we fix the policy? And even here in Champaign, I know in Rolla it's the same thing. In St. Louis, Ameren provides, our public power source, yeah. And Ameren also provides electricity here. So the policy, why doesn't Ameren have more microgrids in the US? Well, obviously one of them is financial, but they actually have a group in Ameren, because I met with them, that study microgrids. But the biggest roadblock for Ameren to implement this is policy. And so going either to, in our case, Jefferson City, right, which is where the state legislature is, or going to Chicago, that's the issue. You have to get involved and change the policy. One of the big issues that they face in Utah, where I'm from, a name like Joseph Smith, Utah is a good state to be from, right? But in Utah, Rocky Mountain Power, who provides, they're like Ameren, they provide electricity in that part of the world. How do you charge for transmission? If you think about it, in my house, I generate electricity and I don't use all the electricity I generate. So I send it back onto the grid. And then I get, at the end of the month, I get my bill and they basically, do a balance. They say, you generated, what megawatt and you consumed 0.9 megawatts. I don't get a check, I get credit. And then at the end of the year, they settle up, right? But there's no money that transfers. And so the system is designed so I intentionally only produce 80% of my annual demand. And that's how the policy works in Rolla, Missouri, personal experience. In Utah, they hadn't figured that out a while back. And so what they did actually, when you put a solar system on the grid, then they charged you a premium for the transmission. So your power bill actually went up and not down. That's backwards. That doesn't incentivize people to use, renewable energy, right? They fixed it since then, but I'm just saying, policy is one of the biggest issues that you have to address. And so here in the Midwest, where we have, this potential, we have enough money, we can do something like that. But the policy sometimes can get in the road. And in Africa, it's no different. The only thing in Africa, and I'm not saying that the government isn't corrupt here, but it's way more corrupt in Africa, okay? So policy is a big deal. And so that's one that has to be addressed first. And then you can see this scale-up financing and the digital knowledge management. And our microgrid in Rolla, we can monitor it remotely. Same thing in Africa. When they put these systems in, they have a central location where they monitor both the load and the generation so they can manage it effectively. So that's this project, this AMD project here. Okay, this is this arena. It's International Renewable Energy Agency green hydrogen. So this is designed to make hydrogen, right? And this is an electrolysis system. And in this case, as opposed to a nuclear reactor, right, they use wind or solar to drive their electrolysis unit. And the great thing about electrolysis is that it's got an infinite turn down rate. So you can put it on a solar system, and when the sun is shining, it's working at full capacity. When it's cloudy and it's not generating, it's not making much. Now you have to have backup so you can make up the difference in the generation. But my point is that renewable energy is a good way. That's a good way to store that energy, is to put it into hydrogen. And so electrolysis, and that's what this whole arena project is developed, it's built around this thing right here. And then again, you've got the other parts of this, the same thing. And if you're interested in just learning more about this, hydrogen generation is a really big deal. And that's something that we're working on. Right now I have a project in my lab, actually, but it's from a company in Detroit that the owner is actually in my lab right now working with my graduate students, making hydrogen from methane. And so you can pyrolyze methane to make hydrogen. And again, it's the reason why would you ever make methane into hydrogen? That makes no sense, right? Well, hydrogen is a good energy storage. And so methane is also, but you can make carbon black from methane as well. So you can make two products, and so you improve the financial performance there. All right. So this is another one of these systems that helped to implement the solar microgrid project in Nambia. So, all right, let me conclude and then we'll take some questions. Energy poverty is a global challenge, something that we all have to deal with. And again, remember what I said, access to stable, reliable energy is the key to peace and prosperity. If you want to do something that will affect the world, work on that, right? 9 out of 10 live in extreme poverty in Africa. That's a focus that we, as engineering societies, nuclear, chemical engineering, mechanical engineering, every engineering society has to focus on because it's such a big deal in the world. We are, as AISHE, as chemical engineers, we're engaged in this global collaboration to try to bring new technology in process-intensified hybrid energy systems to address energy poverty. That's how AISHE is involved in addressing this issue. Okay. Hybrid energy systems offer a sustainable option to address this challenge. And again, nuclear hybrids are the future. You'll see more of that, and you won't. And I don't have it in this. Tomorrow I'm going to give another talk, and I've actually got some pictures of the reactor that's being built in Texas right now that was ordered by Dow Chemical. Dow has ordered one. They're already in construction. It'll be online. There's another one that they've ordered. So they've got 2 nuke plants that will be coming online to provide heat for the chemical plant in Texas. And the Texas operations for Dow is about 52 square miles of chemical plant, and it needs lots of energy. And so that's how they're going to supply that energy, is from nuclear power and nuclear heat. So this is an opportunity to get involved in developing those systems. Nuclear hybrids, again, combine renewable fossil and nuclear to produce electricity, chemicals, and fuel. And then again, what I've shown here in this switch competition, which I recommend if you haven't, if you want to get involved in a fun competition that you can actually make some money at, look up switch competition and get involved in that. But we did this last year, and we identified Nambia for implementation of hybrid system to help reduce energy poverty. And solar microgrids were the recommended solution for that. All right, so here we go, solar microgrids, and I'll leave you with that. Thank you. Yeah. Yeah. Right. Yeah. Good question. And in every place that you have new technology come in, you have to train the workforce first. Several years ago, I was invited by the King of Saudi Arabia to come to Saudi Arabia to help them develop their policy for implementing nuclear power in the kingdom. And the number one first recommendation, they had no nuclear programs in Saudi Arabia. So let's get something going in one of the king universities in Saudi Arabia. That would be good, right? Good place to start workforce development. And so we did. We actually supported developing at King Abdulaziz University a nuclear program to help train for that. So the same thing has to happen at some of these countries like Nambia. We have to be able to go into the universities and support them and help them develop these people that are going to be required to operate these systems. Now, another thing that has happened, and when I lived here in, like I said, I lived in Tuscola and I worked at the Cabot plant, right? And we had a hydrogen plant there because we needed hydrogen for our process to make fumed silica, and it was 100% remotely operated. It had a fence around it. We never touched it, and it generated our hydrogen 24/7, 365. And they would come once a month and do maintenance on it. So that's the other thing that's happening is with new technologies, remote operation has become a real thing. And so we can do that. And it doesn't have to be wired operation, it's wireless operation, right? And again, with things like Starlink, you can actually do that now. It's something that's feasible. So that's two things that you can do, right? Remote operation, workforce development. But that's a very good point. You got to address that issue. Yeah. 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 When I came in here this afternoon, I looked at the desk and they had the battery up there, and I was just reminded yesterday I was in the lab and we were talking about making hydrogen, and I told them when I was a kid, and I had my first chemistry set when I was 8, and so I would get lye and I would take aluminum off the back of gun wrappers and I'd make hydrogen, right? And I would put it in a pop bottle and I'd put a balloon over it and then it would go, and then I would tie a string around it and light it. Right. Hydrogen is very flammable and is very dangerous. One of the great things about chemical engineers is that we focus on process safety. CCPS, which is a big world international organization, about 300 members, is focused on process safety. So that's one of the issues that we have to also consider when we build these systems that are generating hydrogen. How do we do it safely? And there are established process safety guidelines, and so we have to implement those. You can't bypass, you can't short circuit. You've got to do that. Absolutely. Good point. Yeah. Other questions? Oh, go ahead. How do you deal with nuclear waste? Let me start by correcting you. There's no such thing as nuclear waste. How about that? That's a controversial comment, right? Yeah. When you burn fuel, and you can correct me if I'm wrong, yeah. When you burn fuel, you actually take it from a certain enrichment level down to another level. And the current fuel cycle that we use on our nuclear power plants, light water reactors, can only burn a certain fuel to a certain level. And so they have to refuel about every 2 years. In Callaway, they do it about every 2 years. And all the partially burned fuel is stored on site. So in fact, in the US, probably the number one energy resource we have is spent or partially burned fuel. Now, all we need to do is change our fuel cycle and we can process that fuel. And so it's not waste, it's just partially burnt fuel. Okay. Now, how do you deal with that in an SMR? Well, there's some of the SMRs actually have thorium cycles. Some of them have there are different types of fuel cycles and different types of systems that will allow you to have zero waste. Any comments you want to add to that? Right, right. Right. Yeah, yeah. It's just another opportunity, right? But again, it's not the technology that's limiting, it's the policy. And the cost, yeah, but certainly the cost is always involved. But again, the NRC, we work closely with NRC. And the NRC has a lot of policies, right, that we have to deal with. And so one of the issues that, again, with an SMR, one of the issues is if you have a single design that's implemented across the board, then you only need one design permit. And now you have to have site permits for each of the units. But right now, all of our nuclear power plants have two licenses. We have a site license and we have a design license because they're all stick built specific to that site. But with an SMR, you don't have that. Yeah, the modular design allows you to get away from that. So again, policy is a big deal. In China and Russia, by the way, I will just tell you, they don't live by NRC rules, right? That's why China can provide to Kazakhstan a nuclear power plant that will do, $10 a watt, which is really bizarre. That's, when I heard that, I couldn't believe it. So anyway, there you go. You bet. Any other questions? Yeah. Well, I'm going to defer to the expert on that one. I can tell you what I think, but go ahead.
So that study, I know,
Right.
global conditions and how the system you have, so.
Let me show you. This is a picture that I had. I don't know if I can get back to it in time, but here we go, right there. There we go. So just look at each of these designs up here. These are Argentina. This is US Westinghouse. This is B&W, again, US, Holtec US. Here's the South Korea design. NuScale, again, a US. There's China, France, and the US. Okay, so those are kind of the key SMR designs right now. And I will just tell you that Saudi Arabia picked the smart one from South Korea. That's the one they picked. Dow, their system is not even listed here. This is a new one.
Many more.
Yeah, there's a bunch. They're like 50 or so designs, right? And they each have a little bit different, feature. The one that the DOE bet on was NuScale, this one right here. And that was announced and they got the design permit for INL to build one out in the desert in Idaho. And then the backers, the UAMPs, the guys that were going to fund it, backed out. So, unfortunately. But that's the one I thought would be built first. It wasn't. Maybe it will be, I don't know. Yeah. You had one question? Yeah. How does that compare to this? Yeah, be more expensive. The small modular would be more expensive than this, what we proposed here. It's amazing what they've done with solar. I mean, again, mostly because of China. The cost for solar panels, I mean, the panels I use are 450 watts. And again, those are, about 4 by 5, foot. That's a solar panel. And they're about $200 a panel. And 450 watts is pretty high. You can get up to 500 watt panels now. But the prices come down dramatically. It's cheaper to produce electricity from solar than almost anything, including coal. Yeah, I mean, obviously you got to integrate it into a system, and so you got to then control because you have to have backup and the whole thing. My system, like I said, it's got a gas backup for it. Solar by itself, I would say, is cheaper, but then when you have the backup, it goes up. There's more expense for that too. Yeah, good point. Okay.
So maybe we can, I'll just make one comment. So the interesting thing is that the more solar you have, the more expensive the electricity is.
Absolutely.
So, you look at California, look at Germany, wherever renewable percentage is high, electricity is more expensive.
35 cents in Germany.
California, expensive
Yep.
energy.
Yep.
The most amount of solar is in California.
Yep.
So with that, let's thank Professor Smith. Thank you very much.
Thank you. It worked out. I got done in time. I thought I wasn't. Yeah, I'm glad that they.
Sometimes there's just one question, very easy question.